In this problem, we have a set of vectors W, and we have to find what's called a minimal generating set for W. So we're going to find a minimal generating set for W. So what is a minimal generating set? So a minimal generating set, we'll call it S, and we'll say it's a minimal generating set if it has no redundant vectors, so has no redundant vectors. That means that you can't have some of the vectors in S being linear combinations of the others. And also it means that the span of S, so the set of all linear combinations of S, is equal to W. In other words, S spans W and it has no redundant vectors. And if we have those two things, then we have a minimal generating set for W. So we'll start this problem by rewriting W in a more convenient way. So we still have this set of vectors, x1, x sub 2, x sub 3, and I suppose maybe we could subtract x3 from both sides here and just clean this up. So this is really x1 equals minus x3. So I can write it that way. Okay, and then I suppose we can go further and actually make some replacements here. So we can write x1 as negative x3. x2 is simply x2, and x3 is x3. And here, x2 and x3 are real numbers. So x sub 2 and x sub 3 are elements of the set of real numbers. And I think we can break this up even further, right? We can write this as two vectors. Let's see, I think we can do this. Let's try x sub 3 times the vector 1, 0, 1. Right, that's going to give us, and then negative 1, 0, 1. Because when you multiply this times this, that'll give you the negative x3, which we have here. And then x3 times 1 gives you the x3 on the bottom. And then plus x sub 2, just trying to be clever here, 0, 1, 0. And if you look at this for a moment, if you pause and reflect on what we've done, you'll notice that this is exactly the same thing that's written up here. And this is such that x3 and x2 are in the set of real numbers. So W can be written, every element in W can be written as a linear combination of these two vectors. So the set containing these two vectors spans W. So you can, this is basically equal to the span, right? It's the span of the set of all linear combinations of these vectors here. And I think it's clear that there's no redundant vectors, right? We have two vectors, and for there to be redundancy, they would have to be linear combinations of each other. In other words, you'd have to be able to write one vector as a multiple of the other. But if you try to do this, this is impossible because you end up getting this. Or there's no way this can happen. And that means that alpha is 0 always. So it just doesn't work. If alpha is 0, then the whole thing is the 0 vector. And you get negative 1 equals 0 and 1 equals 0. It's just simply silly. So S here, the answer to this question would be the set containing these vectors here. This would be a minimal generating set for W. And again, a minimal generating set is a set that spans the set. So the span of S is equal to W. And none of the vectors here are redundant. In other words, you can't write any of these vectors as linear combinations of the others. I hope this video has made some sense. That's it.